This is Lab 5, Motion of a Falling Slinky. The purpose of this lab is to analyze the motion of a falling slinky, specifically the bottom of the slinky, and compare the actual motion to a computational model. We'll be using Newton's second law. This law states that if the net force on an object is zero, so will the momentum. If the net force is not zero, there will be momentum in the direction of the greater force when working in 1D. We'll be using the position and velocity update formulas, which you can see here. The preview, the bottom of the spring will remain motionless until the top of the spring hits it, and this is because the tension of the spring and the gravitational force acting at the bottom of the spring have an equal magnitude in opposite directions. So here's the tracker view. The system is the Slinky and the Earth. The surroundings is the air resistance. So as you see, when we drop the Slinky, the bottom remains still until the top hits it, and then the whole thing starts falling. You can see the graph here. So here's our initial conditions. This is the initial position vector from tracker, and we use that the glow script code. This is the Slinky's mass. And then here's our GlowScript model. So we use GlowScript so that we can have a computational model for the bottom of the Slinky's motion, since it can be tedious to find the position in real life. So the first while loop is while the bottom of the Slinky is not moving. So we have the force of gravity, the tension, and our net force. And the net force is zero because the gravity and tension have equal magnitudes in opposite directions. And then here we're just using the velocity and update formulas to find its new position and velocity. And then the second while loop is while the bottom of the Slinky is falling down. So we have a new net force. We have drag going up, gravity going down, but the force of gravity is greater than the drag force, so it ultimately moves down. And then we just use our velocity and position update formula again. So here's graphing the two. The predicted position says that it should fall faster than it actually did, and here's some reasons why. So the point could be wrong at each frame, and that's because over 200 frames were analyzed in the experiment. The position of the bottom of the Slinky is likely incorrect in some of those frames, as it gets tedious after a while, and work done by the surroundings. The computational model assumes there is no work done by the surroundings other than the drag force. However, other forces such as wind may do work on the system, making the model predict that the Slinky lands faster than it actually does. So why does the bottom of the Slinky remain still? Until the top of the Slinky hits the bottom of the Slinky, the forces acting on the bottom cancel out. The upward tension force has the same magnitude as the downward gravitational force, so it remains stationary. When the top does hit, there is no longer a tension force acting up. The gravitational force is greater than the drag force, so it moves down at that instant. And what if we attach a mass to the bottom of the Slinky? Would we still see that the bottom remains stationary? Well, here's a video by the same creator, and we see that the bottom does still remain stationary until the top hits it. So as long as the tension acting on the bottom of the spring has the same magnitude as the gravitational force, the bottom will remain stationary.